right. Hello, everyone. How are you doing? I know we are at the last session for the day, 4 days of sessions, and just one more before the party. So anyway, today we are going to talk about App Runner, how you can lower your total cost of operation with App Runner while running highly performant web applications and APIs in AWS Cloud, and while also maintaining the agility of your development, how fastly you build your applications and services. But before we get into the session, I just want to do a quick poll, like how many of you here use containers to run your applications? Maybe a quick hand raise. Okay, and how many of you know or have used ECS or EKS or even self-managed EC2 for running your containers? Nice. And how many of you have used Lambda to run containerized web applications? Okay, nice. And to the service of today's discussion, so how many of you know or have used App Runner to run your web application in AWS? Nice. So I think we can use this session to learn more about App Runner. So yeah. So before we dive into today's session, let's set some agenda. So we are going to discuss about why we built App Runner in the first place. What are the goals? What do we seek to achieve through App Runner as a service? Next, we will discuss all the core capabilities that App Runner provides and that can help you gain agility, run highly performant applications in AWS Cloud, and optimize your total cost of operations. And the best way to drive all these points home is to look into a customer success story. So we'll see a real-world use case, how one of our successful customers used App Runner to build and run their applications on the service. So yeah, let's get started and dive into this. So the first question, why we built App Runner? There are so many different ways of running containers in AWS Cloud, as well as on data centers, on-prem data centers, and other clouds. So what's the need of this service? And to understand that, let's work backwards from our customers and what are the problems that are there when we think of running containerized applications in cloud. So you have your application, you have built your application. Now, to build and deploy it into a container and deploy it on a compute, you need to build and manage a build and deployment pipelines. You also need to think about how you can make sure that your application containers are using latest software packages and they are secure. The next thing is you need to choose your compute. It can be an EC2 instance or a Fargate instance, and you need to choose what's the best fit for you and manage them. Next, while running your containers, you also need to consider what's the container orchestration layer that you want to use and how you want to manage your applications. And now, since while you have all these things figured out for yourself, the next thing is that when your application is running, in order to serve traffic, you need to run multiple copies of these applications. So for that, you need to manage a load balancer. And then to efficiently scale up and down based on the traffic in a cost-optimized way, you need to auto-scale your application. So, and these are just the core components. These are the bare minimum that you need for every application. Then, depending upon your application's use case, and depending upon your organizational security, governance, and control requirements, there may be other resources that you would want to manage to make sure that your application is running securely and in a performant way. So we heard from our customers that while all these things that we saw in the previous slides, it gives you great control over the infrastructure pieces. It gives you the ability to manage the characteristics of your applications to the finer details. but that's a lot of work. We have heard from many customers and developers that they want to focus on application building. They want to quickly iterate and build value-added product and services on AWS. And managing these infrastructure pieces requires a lot of steep learning curve, and it also slows them down in the process. So our customers asked us for a managed way. The other thing is that they also want to scale seamlessly. They do not want to over-provision, they do not want to under-provision, but just the optimum scaling mechanism should be there that is also cost optimized. And if we think from data center, that's another problem. Like you would want to run, when your application reaches a certain scale, you would want to scale that application to meet your traffic needs. And finally, the number one job of building for security. We all want to build and operate our applications in a very secure manner. And doing all these things takes a lot of work, as we saw in the previous slide. And that's why we built App Runner. It's a highly abstracted, fully managed service that enables you to run web applications and APIs in AWS clouds. It's managed by AWS, which essentially means that you do not need to manage Amazon EC2 instances or any compute instance. No need of managing clusters, load balancers, and all those things. It's highly elastic. It scales up and down based on your traffic needs in a very cost-optimized way. It has a very unique granular pricing model that we will see further in our presentation. And finally, it seamlessly integrates with AWS portfolio of services, be it networking, be it certificate management, all those things are very seamlessly integrated with App Runner. So that's why we built App Runner. And let's look under the hood. What are the things that App Runner abstracts from you? So all the things that you are looking at this screen, all the way starting from your build and deployment pipeline to service infrastructure, to your networking resources, all these resources that you are looking at this screen are running in App Runner service account. These are so many things that you need not manage or worry about. So you can focus more on your application, build them, and iterate quickly. So that's a very high-level overview of App Runner. Next, I would like to invite Nathan Peck, our senior developer advocate at AWS, to talk about the core capabilities of App Runner and how you can benefit from these core capabilities. Nathan.
Thank you very much. So looking at this diagram here of all these different pieces, if you're an infrastructure person like me, you maybe get a little bit excited because you're like, wow, there's so much here in the AWS toolkit that I get to play around with and do all the configuration and fine-tune things to my exact specifications. But a lot of people don't want to have to deal with all that, right? They just want to deploy their application and build their business features and make their business successful without having to play around with the AWS toolkit too much. So the idea with App Runner is let's build all the core capabilities into one product that you can configure in one place without necessarily having to build that all out from scratch yourself. And this is very similar to what many large companies end up doing when they have a platform team internally. And the platform team builds out a custom platform on top of EC2 and AWS Fargate or what other services you may want to build on top of, and then offers that to multiple teams within the company. So we're going to look at these core capabilities of the App Runner service and how it glues all these pieces together for you. Starting with deployments. So deployments are generally driven off of code. Obviously you want to deploy code updates. So you have your development teams, they're writing code, they're merging into source code repository. In order to get this running in the cloud, there's a number of things that need to happen. You need to build a container out of that code and push that container to a container registry. You need to deploy that application and roll it out across potentially a whole fleet of instances, and you need to shift traffic over to that new version of the application. So this diagram sort of demonstrates that end-to-end flow there and how all of this works together. And App Runner, you're going to notice, collapses some of those pieces together into one. You can start with just your source code repository, and you can specify that you want to build and deploy code, which could just be native code like a Node.js application, or you can put your own custom Docker file in there, and you can specify your own custom image you would like to deploy. It works both ways. Now, the cool thing is you can auto-deploy on code push with App Runner alone. So normally, you might need to spin up like a code pipeline, you might need to have a Jenkins server, some type of service that sits there and monitors your code repository, and when it sees an update to your code, then it kicks off a build process. When that build process ends, the goal of that build process is for the script inside the build process to deploy the code. Well, App Runner actually has build and release pipelines built inside of it. It also has zero downtime deployments by default. So traditionally, shifting traffic from one version of your application to another application is a little bit scary, because if you're shutting down a piece of code and your client is connected to that application version and the application version turns off, you might end up with drop traffic. You get this little sprinkling of client disconnects that happen during that rolling deploy before all the traffic gets shifted over to the new version of the application. So this is also something that's built inside of App Runner. Traditionally, you might use like a service like Code Deploy or something like that to orchestrate shifting traffic over. Well, App Runner has that built inside of it. Another thing that's built in automatically is rollbacks. So if you're rolling out a piece of code to a server and that code is malfunctioning and crashing, ideally you want to catch that crash and you want to handle it gracefully. If you were sort of orchestrating a deployment by hand, manually SSHing into a machine and loading the new code onto it and then starting the new code up, you would have to be monitoring that with your own eyes. Maybe your PagerDuty goes off and you say, oh no, I need to log back to that machine and fix it. Or maybe you have a third-party service that does that. Well, App Runner does that as well. It's going to see that your application container is failing or crashing or failing health checks. And it's going to go ahead and say, well, I already know what the previous version of the code was. I already know what the previous image was. Let me roll back to that automatically. And last but not least, you want your deployments to be observable, especially if a deployment fails halfway through or there's some unexpected error. You want to know, why did the deployment fail? So App Runner builds those into the deployment as deployment events that you can then query and view inside the App Runner dashboard. You don't have to go to like a third-party place like CloudWatch or anything else. You can just right there in App Runner see the deployment progress, failures, and take action. So let's talk about security as well. Security is obviously highly important for every application, and for App Runner, we want to build on the exact same security concepts that you know and love from other AWS services. So first of all, let's talk about how it works under the hood inside App Runner. App Runner is built on top of Firecracker VMs. This allows each of the containers that you're running inside a Firecracker service to be isolated, not only from other customer workloads, but even from your own other containers that are part of your workload. Every single container has a micro VM boundary around it. So this contrasts with services that run directly on EC2. If you happen to be running multiple containers on EC2 instance, all of those containers are technically sharing the same underlying host operating system. They could be sharing the same host CPU and memory. So Firecracker is going to give you enhanced security and isolation. Out of the box, you didn't even have to think about that, and you just got that per container isolation. App Runner also integrates with IAM roles. So if you're familiar with IAM roles, this is how you give a particular piece of code that's running in the AWS cloud permissions to talk to a limited set of other AWS resources. And on a per service basis, you can say this particular App Runner service is allowed to talk to an S3 bucket that has some data in it. And this service is allowed to talk to a DynamoDB table, but they're not allowed to talk to each other's resources. So you're able to limit the surface area, and this allows you to protect against a situation where someone is able to crack into one of your services. Maybe your service has a 0-day vulnerability that someone is able to exploit remotely. And by getting in there, they get access to your whole system, where you're going to be able to partition these things down to a smaller level of access using IAM roles. Additionally, TLS, encryption, traffic encryption, super important. App Runner does that out of the box. And it even handles your source code in your images with encryption as well as it's building it and making sure that your private company intellectual property is kept safe. Another core capability is observability. So when you're running an application, you want to know what's going on with that application. And one of the traditional challenges of a more fully managed system like App Runner is that because things are not running directly on your account, or you didn't launch everything manually yourself, you don't really have as much visibility into it. So I want to talk a little bit about how the observability for App Runner works and what level of observability you're able to get out of the system. So here is what an App Runner service looks like in general, running on your account. It's going to produce logs and metrics. So this is really designed for analysis of the system via telemetry and via info or debugging logs that get produced out of your application. You're not going to be able to SSH into a particular piece of infrastructure. You're not going to be able to inspect an application process that's running on a host because those hosts are outside your control. They're AWS supplied hosts, micro VMs that are completely under the covers and completely inaccessible to anyone. You're not going to be able to get in there and look at that process directly. But you can look at the artifacts that it does produce, such as logs and metrics, and those will be going into CloudWatch, where you can then inspect them in CloudWatch or inspect them using various third-party tools as well. So there's a lot of different types of logs that are built inside of App Runner. We talked about the deployment logs earlier. These are going to show your build output, any commands that you might be running as part of your build, including your container build to turn your application into a container. There's the application logs. These are like runtime logs. As your application is starting up, it's going to describe how things are going with a startup. You might have application logs that when your application receives a request, it logs a transaction ID for that request, or maybe any events and steps that it takes as part of serving that request. And there's also event logs. So the life cycle of your service. As App Runner starts up a replacement or a new version of your application or shuts down an instance of your application, you're also going to be able to see logs for those. And then metrics. So metrics are super important because you want to know not just that my application is running, but how much is it running? What is it doing in terms of activity? So here are the metrics that are provided by App Runner out of the box. App Runner is keeping track of incoming requests, the concurrency level that you're currently serving. So in other words, how many requests are you serving at any given time? The total number of requests in a particular period. The latency, so how long did it take to get a response back from your application, as well as the number of failures where your application might have returned a status code other than 200. App Runner is also going to give you the number of active instances, so how many instances of your application are running, and their utilization metrics, so how much resources that they're actually using. And for events, there's a number of different ways that you can inspect your system. So there's the service lifecycle events. These are built inside of App Runner. App Runner is going to be keeping track of updates to your service, deployments, scaling activities for you to inspect. And you can kick off other actions in response to this by hooking these logs up to Amazon Event Bridge. And so Amazon Event Bridge is going to be able to trigger other targets like AWS Lambda, ECS, or even an SNS notification, which allows you to do creative things such as when an application instance crashes, maybe because it shut down due to a runtime error, you could trigger a PagerDuty notification to your phones, and one of your developers gets paged that says, oh no, the application crashed, you need to log in there, look at the application logs, figure it out, and fix it. And one of the last but not least options is the API actions as well. So how do you know or keep track of who has touched your system in terms of updating the code? Well, that's something that you can also monitor using AWS CloudTrail. So the last core capability I want to talk about is auto-scaling, because this really is the penultimate feature that I think emphasizes why you might want to use App Runner compared to building it all yourself out of the raw AWS toolkit. So looking at the compute for your application, there's obviously an application instance. This is the running copy of your application inside of App Runner. And this running copy is a container and a micro VM, as we've discussed before. And you can choose how you want to vertically scale it. So by vertically scaling, I mean the size of the container, how much CPU and how much memory you want to give that particular instance of your application. There are a number of different sizes you can choose from, all the way down to a quarter of a CPU, and all the way up to 4 CPUs and 12 gigabytes of memory. So this is a little bit more constrained than perhaps Fargate, where if you've used Fargate, you know you can go up to like 120 gigabytes of memory and 16 vCPUs. So do keep that in mind. In most cases, this should be enough CPU and memory for many workloads, and you can run multiple copies of your application. So this application instance, with its given CPU and memory, is going to be able to serve multiple simultaneous requests. Now, this differs from something like a Lambda function. If you're familiar with a Lambda function, you specify how much memory you want to have. So the Lambda function has a size to it, but each individual function instance is only ever serving a single request at a time. So if multiple simultaneous requests arrive, there are multiple function instances that get spun up in the background. App Runner allows you to specify max concurrency, which is how many simultaneous requests you think that this particular instance of your application can handle using its given CPU and memory. So for example, in many cases, if I was running a Node.js process, I would expect it to be able to handle at least 100, maybe even 200 or 300 concurrent requests at any given time, because the processor is capable of doing a lot while it's waiting on network I/O or waiting on a database query. It can actually pick up another request and start serving another request in that downtime. So the auto-scaling controls to consider are max concurrency, in other words, how many simultaneous requests you think the application can handle, the maximum or the minimum and maximum number of application instances you want to run. You have to run at least one, obviously, if you want to be able to serve web traffic. You don't want the traffic to just get dropped. And you also maybe don't want your costs to skyrocket out of control, so you want to set a maximum. And what App Runner is going to do is it's going to pause and resume application instances based on traffic and based on your concurrent traffic level. So let's explain how this works. So here's a picture from the App Runner dashboard of how you might configure this. You're setting up for concurrency of 80 requests, minimum size of 1 instance and maximum size of 2 instances. And starting out with 1 container, as time goes on, your traffic maybe rises and falls. And you'll see that threshold of 80, which is the sort of payload size where you think that your application can handle 80 requests at any given time. As traffic rises past that, App Runner is going to proactively begin scaling out the number of containers as it sees you approaching the threshold that you specified. Each time the threshold is about to be crossed, and as it gets crossed, it's going to launch another application instance to serve the next threshold. So it's going from 1 container that can serve 80 concurrent requests to 2 containers that can serve 160 concurrent requests, and vice versa. As your traffic goes down, it's going to scale down. Now, when you reach a point where there's no requests being served by your system, App Runner does something that's really cool, and that's that it essentially pauses your application and it stops charging you for CPU. there's a separate charge for CPU and a charge for memory. And the charge for memory is much smaller than the charge for CPU, because obviously running a CPU requires electricity, and memory requires a lot less electricity. So what you're going to see is, for an application that is capable of scaling down to 0 because it has periods where there's very little traffic, you're going to pay a lot less money for running your App Runner instance than you would with a lot of other compute options out there. Now I want to talk a little bit about the traffic load balancing, because that deeply integrates with how that scaling works. So App Runner essentially is powered by an Envoy proxy load balancer that's deployed internally as part of your App Runner service. So this differs from other forms of deployment that you may have used in the past, where you have to run your own application load balancer or network load balancer or API gateway in order to distribute traffic horizontally. App Runner builds that inside of the service, and the Envoy proxy load balancer is sitting there alongside instances of your application container, forming a mesh of sorts where every Envoy proxy is keeping track of how many requests it's serving, and has an overflow queue where it can spill traffic over to the next instance of your application once it starts to reach a limit that you specify. So here's how that works. I reached a point where the single instance of my application container was unable to serve the amount of traffic that I was sending to it, and so it spilled over to the next. And let's say in this case, I've specified that I only ever want to run a maximum of 2 instances of the application. If that second instance also overflows, the Envoy proxy starts returning back a 429 too many requests status code. So this is very important because it means that you can set limits for your application while also protecting your application from traffic bursts. This is unique compared to all the other load balancing options that you may have on AWS, such as application load balancer, network load balancer, and API gateway. All of those attempt to continue distributing traffic across available function instances or available container instances or EC2 instances, no matter whether or not they're actually capable of serving that traffic. And so what you'll tend to see is once you pass a certain threshold, the latency will continue rising and rising and rising until all the clients attempting to use the service get disconnected. Well, with this approach, by having the load balancer capable of shedding traffic and returning a 429 too many requests error back to the client, it gives the client a chance to retry with backoff at a point when the service has actually scaled out horizontally wide enough to be able to handle the amount of traffic that's incoming. Now, one thing to keep in mind is that there is a cold start associated with launching an application instance. If you're familiar with Lambda, you've probably heard about cold starts. Going from a certain number of instances of your application to that many +1 means that you have to get your application code base and binaries or whatever you're using for your application onto some infrastructure somewhere. You got to get it provisioned, you got to make sure it's actually ready to go, and then you can start sending traffic. So it's important to make sure that your cold starts are as small as possible, and the primary mechanism for doing this is making sure your application is as small as possible, because that means you can download it onto another piece of infrastructure and start it up as quickly as humanly possible or machinely possible. So here you see a scenario where traffic is rising over time, and because in the first cold start, the additional instance of the application was able to start up fast enough that there was no shed traffic. In the second instance, there was a longer cold start, and because the application took a long time to start up, there was a few dropped requests. And then in this scenario, we're saying that the max container instances equals 3, so it's not able to scale any more than 3. And so as traffic continues to rise past a certain point where all 3 application instances are at their maximum concurrency capacity, all the rest of the traffic is shed as a 429 too many requests status code. Now, the interesting thing about this model is it allows us to offer a fairly unique pricing model for this particular service. This diagram visualizes how it works. you see a cold start, initial cold start for your application, and then you see requests arrive. The requests are those blue circles. When the request arrives, the application activates, and it activates for a period of a minimum of 1 minute. And it doesn't matter how many requests are arriving during that time period, you're going to pay a flat rate for the CPU and the memory that the application consumes during that time period, whether it's serving one request or many hundreds of concurrent requests. So once again, this does differ from something like Lambda, where you're going to pay an additional small fee per millisecond for each additional function instance that has to spin up to serve more concurrent traffic. But if your application goes 1 minute without receiving any requests, as I discussed before, the App Runner function or the App Runner instance is going to scale back down to no longer charge you for CPU and actually only charge you for memory during that time period. As soon as a single request arrives, the application instance actually reactivates. It starts charging for CPU again, and there is no cold start at that time. It's actually an instantaneous reactivation of the application. So this is also a little bit different from something like Lambda, where you may be familiar with the fact that when a Lambda function does not receive any activity for a while, when it turns off all the way. And then when it cold starts again, it's going to have to re-download the function code onto some application infrastructure and spin it back up, which may be a slightly longer cold start. So with applications that are running inside App Runner, the cold start is front-loaded, and then the pause and reactivation is actually instantaneous from that point forward. So here's how this works alongside with scaling, and I want to show how the pricing model works as you are scaling and then scaling back in. So here we see traffic rising over time, and then at a certain point the traffic ends and there's no more traffic. So what you'll see there is the traffic as it rises causes App Runner to scale out to 2 concurrent application instances. So you go from paying 1 times CPU plus memory to paying 2 times CPU plus memory. But then when the traffic ends and both of these application instances stop receiving requests, they're both going to go deactive, and you're going to be paying only 2 times memory. If this continues for another short period, App Runner may also say, okay, well, we don't even need to run 2. We can scale back down to 1 again, and it'll be only charging 1 times memory. So you'll see that this model works extraordinarily well for applications that are maybe like a business front-end application for a real-life brick-and-mortar business. Everybody's using the application during the daytime as people come in and out of the shop. But then overnight, when all the employees go home, nobody's using this application. There's not really any point in continuing to pay for resources they're not using. You could scale back to only charging for memory during that time period. And also, any type of application that has periods of little to no usage, you're going to see significant cost benefits from being able to use this App Runner platform that bakes all of the pieces inside of itself and scales all the way down to only paying for memory when there's no activity. But don't just take my word for it. Let's hear from some actual customer success stories, the people who have adopted App Runner and what the results were for them.
Thank you, Nathan. So yeah, a lot of details, a lot of goodness. So let's see how all these things come together through a real-world use case from one of our customers. And that customer is Cox Automotive, Inc. Cox Automotive makes buying, selling, owning, or using cars for millions of users simple. And they do it through these many, there are even more brands which are not on this slide, but probably you will recognize a couple of them. And since they have so many touch points with their end users, Cox Auto has a lot of data points, a large set of data that they manage, and they run machine learning models to better serve their customers. So to enable their data scientists and their internal teams to quickly build these machine learning models at a fast pace and in a very cost-optimized way. Cox Auto came up with a central model ops platform engineering team. And the charter for this team was to do for data science what DevOps did for software development. Make it very iterative, make it quick. And they started with answering two big questions that they had back then. One, how can they make sure that they are able to run all these machine learning models as APIs at scale? And the second question that they wanted to answer was, how can they enable their data scientists to quickly build and deploy new machine learning models and iterate at a faster pace without depending upon a central platform engineering team? So those are the two key questions that we'll be looking their journey on AWS. So they look towards AWS. What are the different container offerings there? And back then, App Runner was not a thing yet. So we can strip off App Runner from this list of things. So eventually, they ended up using Amazon ECS as the choice of their platform. And this is a very common standard implementation pattern that they used. So if you can see, most of their resources are running inside their own VPCs. They have their ECT ML model ECS clusters, service discovery, and then they are tying everything end-to-end with networking, starting from their ECR repository all the way up to CloudWatch for logs and metrics. And this worked. But then it came with certain operational complexities. From cost management perspective, they had, with ECS on Fargate or even on EC2, the compute is always on. So you're always paying for the cost of that compute, the minimum compute that you're using 24/7. Their lower environments, the test and the dev environments, they were always over-provisioned and underutilized. And the unique thing about these models is that while you are building and launching new models, you also want your previous models to be available to the consumers and make them available in such a way that there is no performance degradation. So what it essentially meant for them was that they also needed to scale the previous models at near the same capacity that the latest models were running. So again, there was more cost for them. And there were so many different model versions. There were so many different environments. So to manage the cost and monitor all these costs across different model versions, different environments, they had to do additional work, platform engineering work, to monitor cost across all these systems. So that was on the scaling part and cost part. The other problem was with the auto-scaling. With every ECS service, they had to manage multiple scaling rules and policies. And again, when there was a burst traffic pattern, it was fast, but not fast enough to meet their needs. And most importantly, networking. As you saw in the previous slide, they had to tie together a lot of infrastructure pieces. So they required very advanced understanding of AWS networking services, what are the nuances, how they can leverage all these pieces efficiently. But it worked. They were able to build this model ops team, the V1 version 1 platform, and they were running their model ops, building and running their model ops on Amazon ECS. But one of the problems so part one of the question, the big question that they set out to answer was how they can scale, run the models as APIs at scale. They were able to run it at scale, but cost was still a problem. And then the other thing was that their data scientists, since there were all these complexities, their data scientists and internal teams were still dependent on the platform engineering to build new models, deploy new models, and iterate over them. And something new came up. There was this new model ML model that they had, which would spike instantly from tens of requests per second to almost more than 3,000 requests per second. So it was really a busty traffic pattern. And there was no leading indicator that would inform them of auto-scaling policies. So it was really difficult to predict when the traffic is going to come. And the upstream services, which were consuming these ML models, they were very latency sensitive, which means that Cox Auto didn't have much room to implement retries, and if something is not being served, a request is not being served, you can retry and perform all the computation. So these were the problems that they ran into with this new use case. So what was the answer for them? Eventually what they did was they over-provisioned their compute instances, and they ran these compute instances at maximum strength 24/7. So it helped them keep the latency low, meet all the traffic requirements, but the cost was very high. So it was not a durable solution for them. And around the same time, App Runner came into the picture. They learned about the service, and they wanted to give it a try. So they adopted App Runner for one of their models. And this is the implementation pattern that they came up with. It's as simple as that. So in the previous slide, we saw there were so many resources that they were tying together in building and deploying their models. And with App Runner, it got this simplified. And what were the benefits of using App Runner for their model delivery? So it really simplified their operations. So again, going back to the question 1 of running models as API at scale, they were able to solve for the busty traffic. They simply, for the use case that we saw, they over-provisioned the instances. When there was traffic, it was well served. When there was no traffic, their App Runner services scaled to almost 0. So they were not overpaying. They were over-provisioning their compute instances, but not overpaying for unutilized compute. They could also mirror their lower environments to the production, so the testing became efficient. Their previous versions were also scaled similar to the latest version. So overall, going back to the question 1, they were able to run all these models as API at a scale in a very cost-efficient manner. And most importantly, going to the second question, since this model was so simple, their data scientists, they automated all the things. They provided all these automated templates to their data scientists, and their data scientists were able to run free. They were able to iterate quickly, build new models, iterate the existing models, and get to production faster. And this is the verbatim feedback that we got from their principal engineer. And it really nails down both of these problems for them. They were able to, again, to summarize, they were able to run their APIs, model APIs at scale in a very cost-efficient manner, and they were all able to do so in a highly performant and very agile way. So that was Cox Auto for us. Now, if I can summarize all the things that we have discussed today, and what are the things that we can take away from this session, the key benefits that App Runner provides is, the most important, I would say, is increased productivity. You do not need to focus on servers, clusters, load balancers, and so many different infrastructure pieces. You can simply focus on your application and leave all the heavy lifting of managing infrastructure to us. As Nathan showed, flexible deployments, you can start with your source code. You can also start with your container images. App Runner will make sure that the deployment is safe and secure. There is no downtime. App Runner performs blue-green deployment behind the scenes, and it also looks at your container registry or source code repository, and whenever there is a change, it deploys a new version. Auto-scaling is, as Nathan showed, it's a unique thing that you would not get from a traditional load balancers, and it optimizes for your application performance and optimizes for the latency. And finally, some of the other things like security by design, it's built on Firecracker, highly isolated environments, and comes integrated with IAM roles and policies. Observability, you get that out of the box. You do not need to manage a sidecar, run logging and metrics collector agents and all those things. And finally, the pricing. It has a very unique pricing in its sense that you pay for actually what you use, what's the compute that you are going to use for your applications. So yeah, that's App Runner for you. I think we have time, so we can take some questions. And while we do that, please take a moment to fill the survey for this session.